Thank you. All right, my paper was FixedMatch, which is just a cool recent method for doing semi-supervised learning. Yeah, so overview of the paper. It came out just last month from Google Research. And like the headline result here is that they were able to get 78% accuracy on CFAR 10 using one labeled training example per class, which is, yeah, kind of.
Sorry, was that selected arbitrarily or selected?
It was not selected arbitrarily, it was selected to make them look good.
Okay.
So thank you for that important interjection. So there are a couple of caveats, but I assure you the results are extremely impressive. Yeah, so as I said, semi-supervised learning, we'll talk a little bit about that. And the way they achieve this is doing kind of quite a natural combination of two previously known methods, which we'll describe. So what is semi-supervised learning? The motivation for semi-supervised learning is that there are situations where labeling is very expensive, but raw data can be very cheap. Like, for example, if you're driving around with a video camera. And the thing to understand about semi-supervised learning is that it is distinct from few-shot learning in the sense that you don't have few examples of the thing, you have few labeled examples. There still needs to be a whole bunch of unlabeled examples of the thing that you're looking for. So, for example, in this diagram, if the only examples of class white and class black that I have to learn from are these two, then the classifier boundary that I learn is just this vertical line. That's as good as any classifier boundary that I might come up with. But if I have a whole bunch of other labeled data available to me, I can use that to inform my learning of the classifier boundary, because the distribution of the unlabeled data suggests that there's actually some clusters inside this data set, and I can use that to come up with a classifier boundary that's better than the one that I would have come up with if I only had those labeled examples. So that's the distinction between few-shot and semi-supervised. All right, so the first method, which is a method for semi-supervised learning that went into this paper, is so-called pseudo-labeling. So the point of pseudo-labeling is that we've got a few labeled examples. We train some sort of weak model using the few labeled examples that we've got, and then we start to use the weak model to make predictions on unlabeled data that we then treat as if they were the truth. If the model is confident beyond a certain point. So, illustration. I start off with my labeled examples, one black, one white, and I've got all this unlabeled data. Now, the hope is that if the model is trained using just these two data points, it will be confident enough about the data points that are in the vicinity, of the data points that I've got labeled, to label those correctly. And then those form part of our training set. So in effect, we can jump from here to here. We can jump from here to here. And then we can sort of keep going and expand out. And then hopefully, we end up jumping correctly throughout those unlabeled clusters and essentially labeling the entire data set. Now, the risk here is confirmation bias, because in real world problems, the clusters between, the clusters that sort of define the classes are not going to be this neatly separated, right? We're going to have extremely high dimensional problems. Things that are in different classes are going to be closer to the points that we have labeled than the things that are in the corresponding classes, and so on. So this method runs into a problem that it does actually just label things incorrectly, and then it keeps on learning from its incorrect labels that it's generated. So what we're hoping to do is to add another element, another method of learning from the unlabeled data, so that we can improve our confidence without having to jump to data points that would not be correctly labeled by pseudo-labeling. So the second method is this idea of consistency regularization. Now this says that if you have an unlabeled data point and the model is confident about what that data point should be above a certain level, we can apply an augmentation to that data point. So we can twist it around a little bit, flip it, change the colors, invert, just make it look different. And the prediction that the model gives from those two versions of the data point ought to be the same. So example, if I have here a picture of a horse, I can apply one random data augmentation to the picture, and I can apply a second random data augmentation. And then what I'm going to do is enforce that the model makes the same decision about this data point for both of those augmentations. And the effect of this is that the model can start to pick up things about the image that it might not otherwise have paid attention to. So for instance, if my augmentation number 2 crops out just the lower right part of this horse, then the model might be forced to pay attention to other regions of the image, like the hind legs and the tail, in order to decide that this is in fact a horse. Whereas if I had not done that other data augmentation, it might have only focused on the head and always made the decision on that basis. So I'm applying 2 random augmentations in order to induce the model to look at different parts of the image to learn what features are relevant for identifying horses. All right, so FixedMatch is going to combine these 2 ideas of pseudo labeling and consistency regularization. So we start off with like a small labeled data set, only a few data points. We're going to do as much learning on that data set as possible, and then we're going to go and pick some samples out of the unlabeled data set, and then we're going to follow, first of all, the consistency regularization process. So we pick an image which is unlabeled. We apply 2 augmentations to it. One weak augmentation that kind of preserves the general sense of what the image is, and then a strong augmentation. And then we ask the following question. On the weak augmentation, was the model very confident about what that image was? Meaning like it achieved, let's say, greater than 80%, greater than 80% confidence that that image was a horse. And if so, we're going to include that into our pseudo labeled set, and then we're going to do the consistency regularization process, whereby we enforce that the model's predictions on the augmented version of the data set, on the augmented version of the image, becomes close to what we now treat as the true label for that image, which means that we are we're allowing it to learn from the unlabeled data set in the way I mentioned before, which is that this strong augmentation might remove the part of the image that the model was paying attention to previously, so that we're now forcing the model to have a more general understanding of what it means to be a horse. Yeah. Yo, Andy.
Yeah, this is actually my question, it's a comment, but there's a theme that's been happening a lot, and I think there was a bunch of other papers which were doing representation learning, basically trying to learn similar representations, augmentations. I think for images, the knowledge that a particular augmentation is also label preserving, I feel like it's very strong prior.
Yeah.
It's underappreciated how strong the prior actually is.
Yep.
Yeah, exactly. So otherwise you would actually have something definitely more.
Well, I feel like a lot of work in DNNs right now is like finding sneaky ways to bring prior knowledge into CNNs, basically.
Yep.
Yeah, but it's a strong prior, but it's also a very interesting way of coding. Wait. Oh, maybe Adel should, because he's got the mic.
So he's saying that like the fact that when we do a random augmentation, the label should still be the same is like, it's kind of like, it's A, very useful information, and B, kind of fortuitous, right? Is that your point?
And prior.
Prior, yeah.
Yeah. That we didn't learn it through induction. We gave it to the model.
Yeah.
This extra thing. So it's actually like 10 labels and the fact that augmentation works.
Yes.
Or that's input. The input is the 10 labels and the augmentation.
Yeah.
So what you say that we code and we can eye check the augmentations. We know augmentations that will change hoarseness. That is an input to the classifier.
Exactly right.
Hoarseness preserving augmentations in this case.
Or hoarseness preserving functions. Very important mathematics class.
Alrighty, so let's see how this plays out. So we start off, we've only got one image in the labeled set. So that's our labeled set. This is the set of images on which the set of unlabeled images on which the model is confident enough above a certain threshold that it can say what they are to get the pseudo label. And these are the pairs, these are the training pairs that we're gonna train on for this step. So training pairs, we're just gonna take the horse image, augment it a little bit, and then train our model. So the model becomes a little bit better at recognizing horses, fine. Nothing has changed significantly. Same labeled set, there's still, the model is still not confident enough to say that any other image is an image of a horse, so we just go and generate another augmentation, and we keep on training. But at a point, the model will become confident enough about some other image. And it'll say, you know what, I believe with probability greater than tau that this other image, which came from the unlabeled set, is also a horse. So now we are able to do the consistency regularization process, not only with the image that was in our labeled set, but also with the image that was in the unlabeled set. And this now allows the model to learn more about horses than it knew from that one unlabeled image. Like, we started off with an unlabeled image, it had particular characteristics. Now we've been able to add a second image, and we can learn some different things that will hopefully allow us to jump to a third image and a fourth image, and so on. So yeah, we just keep training for a bit, and then the model becomes confident about the next image, and you see like this process proceeds iteratively. Okay, so results, like I said, are impressive, what you can do with this. So with 40 labels, they had an error rate of 13.81, so like 86% accuracy. And the error rate that I mentioned at the start of 22% with one labeled example per class, that is derived by picking the best starting point for each of the classes. So they went through all of CFAR 10, or there's actually papers on this, and they found like the plain picture that is the most plain out of, yeah. So so that's how they got that. If they got a random one, I think they got like 68. Yeah.
Like they've got like a biplane. It's like wings. Wings very important.
Yeah, wings very important. Yeah. Oh no, this is it. This is it.
It's the most plain.
Yeah, absolutely. Yeah. For all 10, by the way. Yeah. So that's the most cat. That's the most horse. Yep. Yeah.
Do they say anything about like how clean your data is, how clean your labels have to be?
How clean your labels have to be.
So it's because this amplifies noise.
Yep.
In the labels.
Yep.
So one of the things, so we actually for like models that we built, we actually use this kind of approach, the pseudo labels as well.
Oh.
And I'm sort of the most vocal. How do you call it? Person who always shits on it. Antagonist.
Critic.
Well, no, I think it actually is antagonist. But anyway, so because I always feel like because our labels are not completely. There's noise in our labels, so I always feel like you're just gonna blow up. All that noise.
So first of all, I mean, they're showing this on CFAR 10, which we all know is perfectly labeled, and in real life, you know, that doesn't generally hold. Completely agree. Like, secondly, this already has a chance of mislabeling things just on its own. Like, even if your data set was perfectly labeled, there would already be a probability that it goes in and mislabels stuff. So, you know, having incorrect labels in the first place would add to that. However, since it's a semi-supervised method, the initial label data set is small. So presumably it would be possible to curate that thing and make it as correct as possible. That would be.
Did they put any math behind it or some?
How you make the decision? It's a hyperparameter. That's yeah.
Selection that parameter, because once you move that parameter, you have
Yeah. Oh yeah, absolutely. Yeah. Yeah.
It must be a good rule. Otherwise, it becomes an engineering.
Well, I mean, I can tell you that the situation how it may turn out to be is that you don't really have a full grasp on ground truth anyway. So then you can always convince yourself that it works. But it's like, I feel like this is where my antagonism comes from. It's just like I just don't trust it.
Well, there's a deep irony. This is evaluated with all the labels. So like any semi-supervised system.
I trust this data set. Like, but I feel like
No, but I mean on a novel data set which doesn't have existing test labels which you can hide, you would not like a posteriori know whether you were doing well or not.
No, exactly. So but they don't really discuss this much in the paper.
I don't recall a discussion of that exact point.
Did they check the jitter when there's a lot of variance when you pick random examples to start with?
Yes, yeah.
It converges nicely. Never mind what the examples are.
No, there's quite a bit of variance. Yeah, I think that they do experiments where they pick like five random starting points, and the variance can be like 20 percentage points of accuracy.
So you need like to have a clear idea of this is the platonic.
Sure.
Right?
Yeah. Or I guess you can pick a few random ones, see how much variance there is in your specific domain, and then try to find.
One of the nice things about this paper is it comes out of Google Research, so they had the resources to do kind of all the obvious experiments that you would expect. So if you're curious, did they try this thing? They probably did. Have a look at the paper.
Was there any discussion of the added cost to train?
No, we looked for that.
Our understanding is that it's not as bad as FixedMatch.
Low bar.
Yeah. Yep. Transfer learning? I would suspect not, because this is CFAR 10, so I'm not sure. Yep. I believe so, yeah. I'm not 100% confident, but yes. The question was, do they use transfer learning here? I think transfer learning would probably defeat the purpose. Yeah. Yep. All right. So let's just keep going. So this idea of like the most bird. This is, they refer to it as prototypicality, and they have some examples of what happens when you have a more and less prototypical training set. So this is the one that we saw before that was as prototypical as could be found, and this one down the bottom here is the least prototypical, and this is a curve of how the accuracy of the trained model went on each of those sets. So it is strongly affected by the starting point. So limitations, as I mentioned before, there's prototypicality. I have kind of a question mark. It wasn't discussed in the paper, but like class imbalance, like if you have many more examples of one thing than of another, which I've heard that can happen. Then I'm not entirely convinced. Like I think it would probably jump to the common class.
The problem is we have a lot of examples of balanced data sets. That's not extrapolation.
Yeah, and once again, another issue that I've read about in books is few-shot learning, where like you really only have this many examples of an object, and you don't have a whole bunch of unlabeled examples to do this semi-supervised process on. It's not going to help you at all. Yeah, that's it.